So 2024 is an exciting year in the field of structural biochemistry. In October, the Nobel Academy announced that the Nobel Prize in Chemistry would be awarded to David Baker of the University of Washington for the development of Rosetta Fold, and shared with John Jumper and Demis Hassabis of Google DeepMind for the development of the artificial intelligence tool Alphafold2. Alphafold2 is an AI-based protein structure prediction system which revolutionized the field by achieving highly accurate predictions of 3D protein structures from amino acid sequences. So the pictures of David Baker, Demis Hassabis, and John Jumper are shown here. And then I will go ahead and bring up this slide to show a little bit how Alphafold2 actually works in systems. So Alphafold2 relies on evolutionary information derived from multi-sequence alignments, or MSAs. This starts by identifying sequences that are homologous to the target sequence, such as sequences with similar ancestry. These homologous sequences provide evolutionary constraints, highlighting residues that co-evolve, often indicating that they're spatially close in the folded protein structure. The core of Alphafold2 is the evoformer, a neural network architecture designed to process two main data types: MSA representation, including information from the MSA, as well as pair representation, describing the relationship between pairs of residues encoding spatial relationships such as predicted distances and orientations between amino acids. After the representations have been refined by the evoformer, Alphafold2 uses a structural model to directly output 3D coordinates of the protein backbone atoms. This module generates atomic level predictions of the protein structure. The entire process is iterative, with the model continuously refining its MSA and pair representations to produce more accurate predictions of the structure. The iterative approach allows Alphafold2 to learn long-range dependencies and improve predictions even for complex proteins. Alphafold2 provides a confidence score for its predictions using a metric which is called PLDDT, or the Predicted Local Distance Difference Test. This estimates the accuracy of the predicted local structure for each residue. Higher PLDDT values indicate a greater confidence in the accuracy in the predicted structure. To summarize all this, Alphafold2 combines evolutionary data in the MSAs, structural templates, and deep learning techniques to predict protein structures with remarkable accuracy. Its use of a sophisticated transformer-based architecture, evoformer, and direct 3D coordinate prediction makes it a very powerful tool in structural biology, transforming how researchers approach protein folding problems. Individual scientists can download the Alphafold2 source code from GitHub, and then they can install it on their own hardware. Although this takes a little bit of time, you need a fairly high amount of hardware. It requires a fairly large amount of RAM and disk space, as well as specialized GPU software as well. So one alternative would be to use the Google Colab through an interface with protein visualization software Chimera X, and that's available as a free download from the University of California at San Francisco. So here I'll be demonstrating how to use the interface to Alphafold2 and Chimera X to predict the structure of Cytochrome C in Skipjack Tuna. The sequence of tuna Cytochrome C can be obtained from the UniProt database online, and the X-ray crystal structure of tuna Cytochrome C can be obtained from the protein data bank using the PDB accession coordinates 1CYC. Now, for predicting a structure, the reason we do this is for verification and validation to make sure we've kind of predicted the correct structure, right? So the first thing we want to do is obtain, well, The first thing we're going to need is we're going to need to go to Uniprot, which this is uniprot.org, and we can do a search for tuna Cytochrome C. And let's just see what we come up with. The very first one is Skipjack Tuna. That is entry number P00025. This is the scientific name, Cassoonus polemus, Skipjack Tuna. It's 1 of 4 amino acids in length. And all we need is the sequence. We need the FASTA file format. So I can kind of click. First of all, we can notice we have the structure available. There's the structure 1CYC. But we're going to use Alphafold to actually predict this. So all I need is the sequence information right here, right? So if I download this is the FASTA file. And so I can go ahead and save this as a FASTA file format. I also have a P0025, and I can also simply just cut and paste. So Control C, we cut and paste, and then we need to launch Chimera X, right? So here's Chimera X, and this time I'm not going to open anything. All I'm going to do is I'm going to go down here to Tools, Structure Prediction, Alphafold, and I'm going to predict. Now here I can do a couple different things, right? So I can fetch, I can do a search. You can simply do a blast search of the sequence and see if it matches any known structures. Alphafold actually doesn't do that because it wants to predict from scratch, de novo. It wants to predict its own structure. So we can kind of click predict. Well, we need to give it a sequence, right? So I'm going to go ahead and just paste Control V. Here's my sequence, and I'm going to click predict. And in order to run this, I need to log in to Google Colab, right? So I'm just going to log in with my information here. There we go. Now I'm logged in. And so this just tells me that this is not authored by Google. It's on Colab. That's okay. We're going to run this anyway. And now when we run it, it executes code. Now the code is actually a Python script. So you can, if you understand Python, you can kind of see the code written here. It might be helpful to bring up the code in a different page because this kind of, let's just see what we've got here. There we go. So it's a little bit easier to see now, right? And so this just kind of tells you a little bit about the Python code that it's running. And if we kind of skip down, it's installing Alphafold on our machine. And if we kind of look at it, this little thing over here kind of tells us a little bit of information. Now you can run, you don't have to have a Colab Pro account. You can run Colab for free, but you're going to be a little bit limited with what you can do. So here we've got, I've got a Colab Pro account, and this tells me how many compute units I'm using, and approximately 1.5 per hour. Got one active session. Tells me the system RAM and other information that I'm using as well too, right? The nice thing now, this interface is this is so this is a little notebook in here which is Python based, right? So it's got all the software that we need to run. So it's actually executing the code on the fly, and then it's going to put all that information. So now we can see that we've installed Colab. We're using a Tesla T4 graphics processor, and now it's installing different code on here as we need. right? Now this doesn't take terribly long to run. It kind of tells me the total run time that it's using down here. So we can just kind of let this run, and then will give us our data, right? Just let it continue. It gives me my total elapsed time that I'm running as well. Now what we're seeing is we've got our first model predicted. Google Colab's going to predict 5 of these models. We can already see, if we look at our estimated PLDDT scores, it's around 97%, so it's very high. This shows us a little bit about the sequence alignment coverage that we have, which again, for the most part, the total number of sequences is very high. This is a very well-studied structure. But it kind of peters off at the N and the C terminus of the protein. So these are the positions there. Here's just an estimated, very rough model that it's going to give us. It will give us a much more detailed model later on, right? And so this is our predicted aligned error. And it's already on model 3. And so it looks like it's stopped at model 3. Now it looks like it's going on to model 4 that it's predicting. So again, it's going to predict 5 models overall. Skipjack Tuna, of course, a fairly simple protein in the electron transport chain. That's Cytochrome C. So this is a fairly well-studied protein. Now, if you remember, Cytochrome C does have a heme group, just like hemoglobin. But the one thing that it will not predict is prosthetic groups, because right now the Alphafold2 software will only handle actual protein sequences, right? There is Alphafold3, which will be that is capable of predicting models with prosthetic groups and other things, as well as we can also predict multiple chains But that's fairly new technology. It hasn't been validated quite as much as of yet. So we don't have as much information there. So now we're downloading our structural predictions. We just downloaded all 5 predictions. And let's just see if we have it. There is our model. So this is all of our information. And so now this is our model of Cytochrome C, right? Now you'll notice it's colored by the PLDDT scores. So the darkest blue is the highest level of confidence predicted. The yellow and the light blue are lower levels of confidence. That's mainly the N and the C terminus, but you'll see that for the most part we've predicted a fairly highly, it's pretty confident in the model that it's predicted. Now that's just the ribbon, so that shows the complete sequence from the N terminus to the C terminus. You can see we have several alpha helices present. What we can then do is if we go to actions, atoms, and show, we can show all the atoms. That's still colored. What I can do is color the atoms by element type so we can see them a little bit better. Now one thing you'll notice is that we have not predicted hydrogens. This just predicts the heavy atoms in the structure, which is mirroring X-ray crystallography. Because again, X-ray crystallography does not see hydrogens, so we kind of mirror that. You can add hydrogens to the model right here by structure editing, add hydrogens, and then we can add all of our hydrogens to the model and we can see where our hydrogens are. We will notice, you will notice there's a big gap right here in the middle. That's where it expects to see the heme group, but there's no heme group present in this model. If we can verify that we have the complete sequence, however, if we go to sequence and show sequence viewer, and then the sequence will appear down here. The sequence I input is up here under Alphafold, and so we start with MGD. So we start with MGD, we end with ATS. Here's ATS over here. So we have 104 amino acid residues in that sequence. So we've got the entire sequence predicted. Now let's superimpose this with the known structure from the protein data bank. And so that structure is 1CYC for Skipjack Tuna. So we can just type in our command open 1CYC. And here's the structure of Skipjack Tuna. Now, let me just kind of select, first of all, my best model and just temporarily make that go away. The first thing we're going to notice is that our Skipjack Tuna, we've got 2 of these present instead of just 1, right? The other thing, if we just look at one of these, and all this means when there's 2 of these is it's viewing the entire space group in the crystal structure, and it just means there's 2 proteins in that one unit cell, right? So it's visualizing the entire unit cell. These should be roughly identical. There may be slight differences in the atoms. The other thing we do see is we have the heme group. So we can kind of see that when we superimpose this, we should see that the heme group kind of agrees as well, right? So let's go ahead and just show again. Here's our other model, and now let's use the matchmaker tool to align that. And so I'm going to go to structure analysis, matchmaker, and we want to align 1CYC with our best model right here. And let's just click OK. And so now it aligned. Again, we can kind of ignore, if I just kind of select all this, and then I can hide those ribbons right there, right? I do have a few little artifacts here, which I'm just going to go ahead and hide. There we go. So we can just make those go away. I think I, for the most part, have it now complete. Now, so we've done an alignment, and let's look at our RMSD. So if we look with our matchmaker, I'm going to zoom in on here. Here's the matchmaker that we ran. And so we aligned best model from Alphafold with 1CYC. And that gives us an alignment score of 490.5. And the RMSD is what I really want to look at. That's the root mean square deviation. And so when we align two structures, if the RMSD, if the structure is aligned perfectly, so all the atoms of the structure match exactly, the RMSD will be 0. The higher from 0 we get, the more deviation in the structure. Generally, anything 1 to 2 to 3 is a very good aligned structure. When you get RMSDs as high as 10 or 20 or 30, there's a lot of differences between those two structures. So here our RMSD is 1.109 angstroms. That's a very high level of agreement between the two structures. It's not perfect. There's a couple of small differences here. For example, some of the side chains, like these lysines over here, right? So the lysines are not quite in the perfect position. One's pointing one direction, another is pointing the opposite direction, right? There's a few more lysines that, lysines got a fairly long chain. It is predicting the backbone, but sometimes when Alphafold does its energy minimization, sometimes the side chains go in different directions. So that's often what we see. Here's some more lysines. The lysines are kind of the biggest thing to kind of look at. The other thing to look at in this structure is to identify our heme group. Now the heme is not present in the Alphafold prediction, but it is present here, right? Now we can make that a space-filling model so we can see. And so what we see in both models, we have a methionine on the top end right here. We can actually kind of highlight this, and then we can label that just to see what we've got. I've got two labels overlapping, but it looks like it's methionine 80. And actually it does have a slight difference, methionine 80 versus 81, so that's interesting. I think that's probably due to a small difference in the actual Cytochrome C structure that it's getting. On the bottom, so let's see here. On the bottom, it's kind of hard to see, but we do have a histidine down here, and so that histidine is histidine 19 or histidine 18 in our other structure, right? So this, I'm looking at the best model. Here's histidine 19, and then that's methionine 81. So I can select both of those, and I'm going to hide everything else. Right? Whoops! I wanted to show that. But I want to, if I invert the selection, right? Invert that selection. Now I can hide everything else, right? So now I'm just showing the atoms of those methionines, right? And now let's go to Tools, Sequence Viewer, and let's look at the sequence of chain A, right? And here's the sequence of chain A. We do notice that for one, in Alphafold it starts with MGD, this starts with GDV. So we are missing that methionine at residue 1 in our X-ray crystal structure, but Alphafold put that in. So that's just one reason. That's probably also why Alphafold is slightly less confident in its prediction with that particular methionine, right? So that might be one of those factors there. And we can see a fairly good agreement. Of course, it's not perfect, but it kind of tells us that we can use Alphafold to predict the proteins, and we can predict those structures. So I hope you've enjoyed this video, and now we kind of understand it's relatively simple to do a protein structure prediction, but there are some cautions and warnings that you do want to kind of look at the overall structure for your own confidence, and so don't just take everything automatically.